Okay, hello everyone. Welcome to today's lecture. So this recording is basically for week 4, day 1, but you should watch it after attending or watching the video of lecture week 4, day 2. Why? Because the content covered in this video is built upon the content which we covered in week 4, day 2, right? And that's the reason. And the access code for class participation form, I will share it towards the end of the video. Okay. So remember that in week 4, day 2, we talked about dependencies between instructions read after write, write after write, and write after read. And we also talked about how these dependencies are important when we are trying to achieve the out of order execution, where we want to allow the younger independent instructions to go ahead without waiting for the older instruction to complete and start their execution, right? So to achieve that, we to achieve the out of order execution, or to now we know what is the concept of out of order execution, but how it is actually implemented in hardware. For that, we use the Tomasulo's algorithm. So the one thing which is important in understanding Tomasulo's algorithm is the register alias table, or RAT. So this is just a slight variation of the register file. In register file, we have registers which hold the content, but in register alias table or RAT, what we do is that for each register, we have we maintain two additional information. Other than the value which is placed in the register, we have tag and the valid bit. The valid bit tells us whether the content in the register is valid or not. If 0, it is not valid. If 1, it is valid. And tag, it is used for indexing the reorder buffer. Now remember that reorder buffer is important when we want to do the register renaming, and we want to when we want to commit the instructions according to the program order. Remember, the pipeline which we covered yesterday very briefly consists of 5 stages: fetch, decode, execute and writing the result in reorder buffer, which is indicated by R, and then writing the result in the register file, all the memory, which is indicated by W. So this R stage is the stage where we use the reorder buffer, and using reorder buffer ensures that the instructions are uh, committed according to the program order. So the execution is out of order, but the result of execution, they are committed to the register or the or memory according to the program order, and how it is achieved using reorder buffer. Okay, so first, we've just focused on register alias table or RAT. So for each register, each register has content, and in addition to that, we have a valid bit and the tag. And again, tag is used to index the reorder buffer. Now, what are the contents of the reorder buffer? So the content in each entry of the reorder buffer, it has following information: whether this entry is valid or not, right? Uh, and it also hold. So actually, an entry is created for an instruction as in the reorder buffer as soon as it starts into the decode stage. So when it enters in the decode stage, then the entry of that instruction, the reorder buffer, is marked as valid, right? And then we record in this second column the destination register of that instruction. And in third column, we have the value which is supposed to be written in that destination register. And fourth column tells us whether we have actually written that value into the destination register or not yet. Okay. So this reorder buffer is basically implemented as a cyclic buffer. So we have like maintained two pointers. So one pointer indicates the oldest instruction in the cycle and cyclic buffer, and the second pointer indicates the youngest instruction. So the new instruction which will be placed in this reorder buffer will hold the entry pointed by this youngest instruction pointer, and the instruction that will be allowed to commit, which means it will be allowed to write its result in the register or the memory, will be the one which is the oldest instruction. Okay. Okay. Now, this slide basically shows the textual form of the Thomas's algorithm. I'm not going to read it because it will not make any sense to read it because without explaining it, without showing how it actually works. So what we are going to do is that you can see the simulation of the algorithm and then come back to this slide and read it. And I'm like quite sure that if you do that, then at that time point it will make sense to you. So I'm not reading it for you. You can do it on your own. So here is the simulation of Tomasulo's algorithm, which allows to achieve the out of order execution. Remember, instructions are will be still fetched and decoded according to the program order. However, the execution will be not according to the program order. It will be different. So that's why we say it will be out of order execution. Okay, and in this simulation we are initially assuming that we are not using reorder buffer, which mean that register and the instructions will also committed in out of order, which is not which should not be done. But to keep our understanding simple, we first assume there is no reorder buffer, so instructions will also commit their results to register the memory out of order. Okay, and then we later add reorder buffer to our simulation. So the program we are going to simulate is the execution of the program we are going to simulate is this one, right? In the left side, you have the register alias table. You have register alias table, and in this table, first column shows you the name of the registers R1 to R11. Initially, content of all the registers is valid, and we have some arbitrary values from 1 to 11 for these registers. In addition to that, we have two functional unit, an adder and a multiplier, right? And each functional unit generates two output value of the operation, result of the operation, and the tag. We will see how tag is generated later on. In addition to for each functional unit, we have reservation stations. So, for example, for adder, we have four reservation stations labeled as A, B, C, and D. And in each reservation station, we can hold the source operands of an instruction. So, if an instruction has two source operands, source one and source two, we have the place here. So, this will show that whether the content is valid, the source is valid or not. If valid, what is its value? And if it is not valid, then we will have a tag here. Same goes for the source too. Similarly, here we have four reservation stations for the multiplier. Okay, now let's go through the simulation of uh, our program. So initially at cycle 0, we no instruction is in the pipeline. Uh, why is Yeah, and in cycle 1, we fetch the first instruction, right? In cycle 2, the first instruction enters the decode stage. When an instruction is in the decode stage, when an instruction is in the decode stage, then we need to decode the instruction and allocate it into a reservation station, right? How we are going to do this? First, we will check if a reservation station is available. So since this instruction is multiplier, so we'll check if the reservation station for multiplier is available. Yes, all four stations are empty. So we are good. In step 2, what we'll do is that we access the register alias table. So what we do is that we will put the source registers into reservation station X. So first source register is R1. So we are putting its value. So since it is valid here, so we are putting 1 in the valid bit in the X reservation station for source 1, and we are putting the value which is 1 here, right? And then we will do same thing with the second source register R2. So we are just moving the values. And then what we need to do is that we need to rename this register's output register R3. How we are going to rename? By simply, so remember initially R3 is valid. So what we are going to do, we now mark it as invalid, right? And we will record here the tag of the reservation station which is holding the source operands for this instruction. So what is that tag? The tag is X, right? So what we did is that here we mark that R3, the content of R3 is now invalid, and we are recording the tag of the reservation station, which holds the uh, source operands of this instruction. So effectively, what we have done is that we have renamed R3 to the X. So R3 is supposed to hold the output of this multiplier, right? And now we are saying that the out will be provided by the multiplier once it is fed with the sources of the reservation station X. That's why we are storing here the tag X. Okay. So its new value will be produced by the reservation station that is identified by tag X. So multiplier in reservation station X is ready to execute in the next cycle since both of the source operands are valid now, right? So in the next cycle, this instruction, multiply instruction, can enter the execute stage. So in cycle 3, this instruction multiply enters the execute stage. Now remember that for a multiply instruction, it takes 6 cycles. So that's why the instruction will stay in the execute stage for 6 cycles. So basically what we are saying, it takes 6 cycles to calculate the product or compute the product of the two numbers, right? So here what we do is that we check the readiness. If both of the operands are ready, what we do is that we perform the wake up. So wake up mean that we allow that instruction to go to the functional unit or multiplier. So we dispatch it the instruction to the multiplier unit, and then it will take 6 cycles to complete. And then the next instruction add it moves to from stage to the decode stage. And then add is also decoded using the same procedure. So for add, what is the source operand R3. Now R3 is invalid. So we move validity information into the reservation station for the adder. And since the value is not available, so what we do is that we record the tag here because value is not available. We record or move the tag in the reservation station A. Then we do the same thing with the second operand. So second operand is R4. Now when you look at R4, it is valid, right? So we copy the validity information here, and we also copy the value of that register in the reservation station A. However, since both bits are not valid, one is 0 and the other is 1, since it's mean that both of the operands are not available, so we need to wait, which means that this instruction cannot start execution. So now we need to do the same steps for renaming step for the add instruction as well. So what we do is that the output register is R5. So we look at R5, and now the R5 we are marking it as, and we will mark it as invalid, and we will record the tag of the reservation station. So here now R5 is invalid, and we recorded the tag of the reservation station. And then in the same cycle, the third instruction, which is second add instruction, it will be fetched. So the first add cannot execute because both operands are not available. One is valid and the other is invalid here, right? So we need to wait until it becomes valid. In fourth cycle, our multiply instructions enters in the second execution stage. Uh, Add cannot continue because one of the source operand is still invalid. The second add, or the third instruction, which is add, it is decoded. Now again, we need to do the same thing. So we look at first we look at R2 source and then move the information into the empty reservation station for the adder, right? So R2 is valid and its value is also available. That's fine. Then we look at the next R6, and we need to move its information also. So we get 1 and 6. So it is also valid. It's mean that both of the operands are available. However, we cannot start execution yet because in the same cycle, what we need to do is that we also need to rename R7, right? So how we do that? We actually uh, we mark R7 as invalid, and then in the tag we record the ID of the reservation station B. Okay, and then the next instruction, which is the third add, this one is also fetched. Now in cycle 5, this enters in the E3. It cannot add cannot continue, and now since both of the operands are available for this add, so we send it to the uh, adder, and it will take 4 cycles to compute the summation, or to compute the sum, right? And then in the same cycle, the third add, this one will enter the decode stage, right? So we need to do the same thing again. So if it enters the decode stage, so what is the source register? R8. So is R8 valid? Yes. And we have also its value available. So we move it in the source one field of reservation status C. And for R9, we look at R9, it is also valid, and we have the value available. So we move the information into the reservation status C, right? And then for the output R10, we need to rename R10 register. So here we mark it as invalid. So output registers are always marked invalid initially. And then in the tag column, we record the ID of the reservation status C, right? And it's mean now, since both of these bits are 1, right? So it's mean that this add instruction is ready to be executed, right? In the next, ready to enter the execute stage in the next cycle, right? And then the multiply instruction is enters the fetch stage in cycle 5. Now in 6, this enters in the E4 execution stage 4. Add cannot continue because it still has one of the operand is not available. Second add is already executing and it is in execute stage 2. Third add, it will now enter in the execute stage, right? So what will happen that 8 and 9, they will be summed together, and but it will take 4 stages, 4 cycles to complete it. And then the multiply instruction, it will enter the decode stage. When it enters the decode stage, we need to do what? We look at R7. Now is R7 valid? No. So it has tag, right? So we copy 0 here as 0 and B information, right? This information, we are copying it into the station Y, source one of reservation station Y. Then we look at R10. Is R10 valid? No, R10 is also not valid. So we simply copy the information in the reservation station Y, source 2 field of reservation station Y, right? And then we need to also rename R11, right? So we mark R11 as invalid, and then in the tag area, we record the ID of the reservation station. So we are now using the reservation instruction of multiplier because it is a multiply instruction, right? And then the last instruction add is fetched in the same cycle. Now in cycle 7, this enters the E5 stage. This is still waiting because its operand is not valid, not ready. Second add enters the E3 stage. This enters the E2 stage, and multiply, it cannot execute. Why? Second multiply. Why it cannot execute? Because one of both of its operands are not valid, right? They are not available. And then add enters the decode stage. When add enters the decode stage, we again need to do what? Same thing. We look at R5. Is R5 valid? No. So we have this information. We move it into the uh, so here, before I wanted to show the R5 is 0A, right? So we move it to reservation station here. Like here you will get 0 and tag will be A, right? So as you can see here, and R11, it is also like simply we copy the information into the reservation station D, right? And then we also need to rename our output register R5, right? So in previously R5 was using the tag of A, but now who will be producing R5? The R5 will be produced by the instruction whose operands are stored in the reservation station D. That's why the tag is updated from A to D. Previously it was A, but here we have updated to D. Okay. So it's basically mean that uh, two different instructions are writing to the register R5 at two different times, right? So the first writer of R5 is the first add, and the last writer of second writer of the R5 is the last add instruction. So now by this cycle, we have decoded all 6 instructions, Note that we what happened to R, we renamed it twice. First it was renamed to A, tag A, and then to tag D. Now, interesting things will happen from here. So, and cycle 6, uh, multiply instruction enters E6 stage. So when it enters the E6 stage, so what will happen is that it will produce two things. It will produce the result of operation, which is 2, 1 times 2 is 2, and it will also produce the tag of which is basically the ID of the reservation station, right? So it will simply forward the ID of the reservation, which will be used as the tag. And then this tag is compared across uh, tag column of the rat, right? And it is also compared with columns of all the tag columns in the reservation station, right? So and then we note the locations where we have the match, right? So what tag was produced? X was produced, right? And we got a matched here, and we also got a match in this row, right? So what we will do now, that we will first propagate the result, right? And put the value in those rows where we have the matching tag, right? So we had a matching tag here. We set the value equal to 2. We set the value equal to 2 here, right? And we also mark that now the information is valid. So we mark R3 as a valid, it has valid content, and here the one means that the first source operand is now available. What does it mean? It means that in the next instruction, in the next cycle, this instruction is now ready to be executed, right? Which was this instruction? It was first add, right? So this first add which was stored in the reservation status A, reservation station A. Now it has become available to be executed, right? So Uh, but the add will become available or ready to execute in next cycle, not in the same cycle, right? So that's why here it is still waiting. And then this add enters the E4, and when it enters the E4, remember add takes the 4 cycles, right? So now the results are available. So 2 plus 6 is 8, and the tag is also produced, which is the ID of the reservation station. And we again do the same thing. We compare this tag with with all the values in the tag column of the rat, and with all the values in the uh, tag columns of the reservation stations here, right? And whenever we get a match, we have a matching, we put the value in that in that field, and also mark it valid. So here we get a matching, right? And we also get a matching in the reservation station Y of the multiplier, right? So what we are going to do is that next we broadcasted the result, right? And what we are now broadcasting the result and copying it in all the locations where we had a matching tag, and also marking the valid bit 1, right? So this one of the source operand becomes ready, but we can still not execute the second multiply instruction. Why? Because one of its operands, source 2, is still not available. So in the same cycle, the third add will enter the execution stage 3, and multiply cannot execute because it is not yet, it's one of its source operand is not available. And the last add can also not execute because both of its source operands are still not available. Okay, now here, remember, we don't have R stage. We are not using reorder buffer. We have only fetch, decode, execute, and write back stage. So in this stage, what happens that the result will be written back into the register file, right? So we have already written the result. So this instruction is now committed or retired, right? And then uh, remember that our add instruction, first add instruction was became ready to execute in the previous cycle. Now we can now dispatch it to the functional unit. Now it will be dispatched to the functional unit and it will start executing, and it will take 4 cycles for it to complete. And second add, it is also completed, so it enters the write back stage. And we have already updated its register R7, right? See, it had correct value. Okay. And add, it enters the E4. So when it enters the execution stage 4 is completed, so it broadcasts the broadcast and update the tag and value, right? So what this was like our third add instruction, this one, right? So 8 plus 9 will be the result, and tag will be C. So now C will be broadcasted. Where is Okay, C is not used anywhere, right? So here we don't have, here we have D, here we have Y, right? And here we have tag A and tag Y, right? So C is used not anywhere. So that's why the results are not, we only update we will only update the register in the next cycle, right? So what is the register? The register is 10, right? So it actually we are updating it here. So the value of the register becomes 17. Yeah, here actually we had C. So yeah, sorry for missing it. So here we have C, so we have a matching, and but in the reservation station we don't have tag C anywhere. So this register is updated to 17. Its content is updated and it is marked as valid. Okay. And our multiply and last add, they are still waiting because their operands are not ready, right? So wait a minute. Yeah, so here also in the reservation station we had the matching taxi. That's why it was updated to 1 and 17, right? Now our this multiply instruction is has both of its operand available, so it can start executing in the next cycle. But our last add, it is still waiting. It is still has this, these operands are not available, invalid, so it still needs to wait. Now in the next cycle, fetch will enter in the second execution stage, add will enter in the second execution stage. First multiply and second add, they are already done. Add will enter into the write back stage, which means it has already basically written the results, so the instruction is retired. And multiply enters into the first E1 execution stage. It will take in total 6 cycles, and then its result will be available. So nothing interesting is happening in the cycle number 11. In cycle number 12, our uh, add instruction gets completed. So the this add instruction gets completed, right? So no, not this one. Sorry, uh, not this one. The first add instruction gets completed, right? So 2 plus 4 is 6, and the tag is A. So what we will see that, do we have any matching tag here? Yes, we have a matching tag here, right? So what we will do is like we will only update in the reservation station, right? So here now we update it as 1 and we put the value 6, right? So but still our last add instruction is not ready because one of the operand is not available yet, right? So these two instructions are already completed, so we don't need to do anything. So multiplier enters in the next execution stage. Last adder is still waiting. Here, this execute instruction is completed, so it enters the commit stage. Now multiplier is in E4, then it enters the E5, then it enters the E6. Now when it enters the E6, so this is the multiplier. Now it's going to enter the E6. So what is its tag Y, and what will be the result? 8 times 17. You can do the math, right? So do we have any matching tags? Here we have a matching tag here, and we have a matching tag here, right? So now these two entries locations need to be updated, right? So here we get 136, which is product of 8 times 17, right? And we mark this valid. Similarly, we mark this register as valid and we put the value 136 here. Now in next instruction cycle, last add is ready to execute. In next cycle, this multiply enters the commits stage, W, and then add enters the execute stage. So it will take 4 cycles to execute E1, E2, E3. And then in E4, what will happen? That result will be produced 6 plus 136, and the tag is D. So do we have a matching tag anywhere? Yes, we have one location where we have a tag matching tag. So then it will be updated, right? So 142. And this completes our simulation, right? So this is now how you do the out of order execution of your hardware does the out of order execution, right? Now, here is the interesting thing. Uh, all our instructions they are fetched and decoded according to the program order. So here you can see the green circles. So the program order is 1 2 3 4 5 6. So here you can see first is fetched, second is fetched, third is fetched, fourth is fetched, fifth is fetched, sixth is fetched. However, the the they are not committed, the instructions are not committed according to the program order, and but that is the requirement. What we want to fetch and decode according to the program order. We want to execute the instruction out of order, but we want the instructions to commit, which mean to write their result into the register file again according to the program order, which is not the property not satisfied by this simulation. Why? Because here you can see that first instruction one is committing, then the instruction actually instruction 1 and instruction 3 they commit at the same time, like in cycle number 9, and then in cycle number 11 instruction 4 is committed, and then in instruction cycle number 13 instruction 2 is committed, and then instruction cycle number 16 instruction 5 is committing, and then in cycle number 20 last instruction is committing. So the commit order is not same as the program order. It should be like one, it should be same as shown here, right? But it is not same, right? So here first uh, instruction 1, let me name it as like A, B, C. So commit order, so A, B, C, D, E, F. So instructions are fetched in this order, like first instruction A, then B, then C, then D. But what is the commit order? The commit order is A and C, they are committed first, then B, then D, then not sorry. I don't know how to let me erase it quickly. Yeah. Mm, yeah. First A and C are committed, then D is committed, then B is committed, then E is committed, and then F. So this is not in order commit. Okay. So we want only execution to be out of order, but we want the that instructions are committed in order, right? How can we achieve that? To achieve that, we basically need to use an in order buffer. We need to use a reorder buffer. Okay. Since we are not having questions, so now I can see that I'm going fast. Okay. So reorder buffer. So what is the idea? So the idea is that we want to complete the instructions, which mean execution of the instructions out of order, but we reorder them before making results visible to the architectural state, which means before making the results visible or before writing them in the register file or in the memory, right? So how we do this? That uh, if we just give a pictorial figure of the pipeline, so we have like instruction cache, register file, functional unit, but then we write the results not back from functional unit to the register file or to the memory. We write the results first into the reorder buffer, and then from the reorder buffer, we write the results into the register file, right? So When instruction is decoded, it reserves the next sequential entry in a special buffer called the reorder buffer. So whenever you decode an instruction, you reserve an entry for it in the reorder buffer. And when the instruction it complete, its execution is complete, you write the result in the reorder buffer entry. You don't write the result in the register file or in the memory. When the instruction completes its execution, you write the result in the reorder buffer. And when the instruction becomes is the oldest instruction among all the instructions in the reorder buffer, at that time we allow it to write its results into the register file or into the memory. And this is known as committing or retiring an instruction. So I will be using these terms interchangeably, retiring or committing. Okay. And an instruction retires or commits only when it is the oldest instruction in the reorder buffer. So what is a reorder buffer? So reorder buffer is a hardware structure, and it keeps all the information that is it keeps the information about instructions when they are decoded, uh, but only those instructions which are decoded but not yet committed, okay, are not retired. So what is the information you have in each entry? You will have a valid bit which will tell whether this entry is content of this entry is valid or not. Then the second field, a second column will hold the ID of the destination register in which the result of an instruction is supposed to be written. The third column will actually hold the value which is produced by execution of the instruction and the result which is supposed to be written in the destination register, right? And the next column tells us whether the result is actually has been written in the destination register or not yet. Okay. Okay. So now we are going to use the exact same program which we used earlier. We are going to simulate it, but this time we include the reorder buffer. We assume that now our hardware has the reorder buffer, and we will still this time, since we are using reorder buffer, we will be able to fetch and decode instructions according to the program order, execute them out of order, and then retire or commit them according to the program order. Okay. How I will you will understand when I will walk you through this simulation, right? So again, initially you have register, all the content of all the register is valid. You have these 15 entries in the reorder buffer, all the entries are invalid, right? So when in cycle 1 the multiply instruction is fetched, in cycle 2 the multiply instruction is decoded. Now here is something which is interesting and different happening from the previous simulation where we were not using reorder buffer. Now when we decode an instruction, so some things are similar. What is similar? So we look at R1. So is R1 valid? Yes, R1 was valid and we have its value available. We look at R2. Is R2 valid? Yes. So we also have its value available. And then we will name R3. So first we'll move the sources into the reservation station, right? So first source is valid, its value is 1. Second source is valid, its value is 2, right? But but at the same time, when as an instruction enters the decode stage, we reserve an entry for it. So this instruction goes into the first entry. So we mark that entry as valid. In destination register field, we record R3, right? We don't know what is the what value will be written into this R3 because we have not yet completed the execution of this instruction multiplier. So we are leaving the field empty. And this indicate that the result which is not yet written back into the destination register R3, right? Not only that, one more thing we are doing here is that in the reservation stations, we have an extra field which we are naming it as destination ROB tag. So what we record here is basically the entry number of the reorder buffer, uh, number of the entry in the reorder buffer which is reserved for this instruction. So what is that number? 0. So we simply recorded 0 here, right? The other thing is that here the tags which we will be using will not be the IDs of reservation stations, but we will be using IDs of the entries in the reorder buffer as tags, right? So that's why I renamed this as rob tag, and here also rob tag, rob tag, rob tag, and reorder buffer tag. Okay. So the output register is R3, so we are renaming the R3s by marking it invalid and recording the tag. What is the tag? Tag is the number of the entry in the reorder buffer which is reserved for this instruction, which is 0, right? That's why we place 0 here. Okay. And though I have not raised this 3, but since the valid bit is 0, it's mean that we cannot use this value 3. Okay. Okay. So, and the add instruction enters the fetch stage. Now, since all the operands, both of the operands of this multiply instruction are available, so in next cycle, it can enter the execution stage. So it enters the E1, again, it will take 6 cycles, right? And add enters the decode stage. Now, since it is entering the decode stage, we do the exactly same thing. We reserve an entry for it, we mark it valid, we record its destination register. We don't know yet what will be the value written in this destination register, and whatever value it will be, it is not yet written in the destination register, right? And similarly for R3, what we do is that we looked at R3, so it was like here, it was not valid. So I'm simply, we will copy 00 into the reservation station, right? And R4, it was valid and its value was 4. We simply moved it into the, copied it in the reservation station, right? But in the destination field, destination rob tag, we recorded 1. Why 1? Because this is the entry which is reserved for the add instruction. Entry of the rob which is reserved for the add instruction, right? And then we do also renaming for R5. How? So R5 was initially 1 and 5. So we mark it as an invalid, and in the tag, we record the entry number of the reorder buffer, which is reserved for the add instruction 1, right? This one here. And then the next enters the fetch, not then, but in the same cycle, the next add enters the fetch stage. So multiply will still be in execution. Decode add cannot execute. Why it cannot execute? Because one of its operand is not available yet. Okay. So, and then the third instruction enters the decode stage. So when it enters the decode stage, what we do is again the same thing. We will create an entry here, right? So it becomes valid. We record here the destination name of the destination register R7. We don't know what will be produced as a result of this instruction execution, so we keep it empty, and that whatever result it will be, it is not yet written in the R7, right? And then here R2 is valid and its value is 2. R6 is valid and its value is 6, right? So we simply copy them over here. First source, second source, both are valid. So this instruction is going to be to start execution in the next cycle. And the other thing is that R7 is the output. So we need to rename. So we set it as invalid and we record the tag of the ROB entry here, this tag. Tag is basically the entry number which is reserved for this add instruction, right? And add again enters the fetch stage. Note the difference here is that we are using the entry numbers of reorder buffer as tags. We are not using the IDs of the reservation stations as tags. So multiply enters the next execute stage. Add is still waiting. First add is still waiting, right? So second add, it can start execution because both of its operand were available. So it enters E1. And then third add, it is starts decoding. It enters the decoding stage. So when it enters the decoding stage, here we will resolve a new entry. So we mark it, it's valid. We record R10 as its output register. and we don't know what will be the value written in there, and we know that value is not yet written, right? And we also looked at R8 and R9. So R8 is valid and its value is 8. R9 is valid, its value is 9. So we simply moved them, copied them here, like 1 8 and 1 9 in the reservation station, right? And we also need to rename R10 in the RAT, right? So we set its validity bit equal to 0, and we recorded 3, which is basically the entry number which is of the ROB, which is reserved for this add instruction. Now, this instruction, since both of its operands are available, it is ready to execute in next cycle. And multiply instruction is fetched in the same cycle. So first multiply is still executing. First add is waiting, right? And second add is executing. Third add starts executing here, enters the E1, right? And then multiply enters the decode stage. So when it enters the decode stage, again, here we will reserve an entry for it, and we record R11 as the destination register for multiply. We don't know what will be written here, but we know that it is not yet written in the R11, right? And we also looked at R7 and R18. So when we look at R7, so we have 0 and 2, so it is invalid, and R10 is also invalid, right? So we copy this information into the reservation station here along with the tags, right? So it's mean that this multiply instruction is not ready to execute because both of its sources are invalid yet, right? And also we need to rename R11, right? So how we what we for that what we did, we mark it invalid in the RAT, and we recorded the entry number, its entry number in the ROB, which is 4. And then add instruction, last add instruction, it enters the fetch stage. Okay, next cycle, multiply is still executing, add is still waiting, second add is executing, third add is executing, multiply, it cannot execute. Why? Because both of the source operands are not available. Okay, so it is still waiting. And then add enters the decode stage. So when add enters the decode stage, we will reserve the next entry, right? So we mark it valid. We recorded R5 as the output register, and we don't know what will be the value produced by this instruction, but we know whatever will be produced is not yet written in R5. And also we looked at R5 here. So when we look at R5, so we get the value 0 1 here, and we look at R11. So when we look at the R11, we get 0 4. We will now what we will do is that we will copy them into the reservation station, this reservation station, right? So we simply copied it over here, 0 1 and 0 4, which mean that both are not available, right? And again, we are also, for every instruction, we are in the reservation station, we are also storing the tag, or ROB tag. So for example, for this one, the ROB tag is 5, right? Okay, and also we need to do renaming for R5, right? So R5 was originally 0 1, but uh, for add instruction, now R5 is the R5, this last instruction is the writer of the add, right? So what we will need to do is that we need to update this tag, right? So who will be the now latest producer? 5. So we are going to, yeah. So here we recorded the latest tag, right? So this tag is basically pointing to the instruction which will be the latest writer of the R5. And it will be this one, last add, right? Remember, two adds are writing results into the R5, right? So before this point, we were recording 1. But once we have reached at this instruction and we have reserved an entry for it, we updated the tag for the R5 from 1 to 5. So ROB tag for R5 in RAT is changed from 1 to 5. that is tag of ROB entry, which is latest producer of R5 in the program order. Also note that R5 appears two times in two ROB entries. So once here R5 and here, right? Now we will going to have some interesting things here. So now first instruction is has completed executing E6, right? So if it has completed, so which one was it? Was first multiply, right? This one. So we look at we go to that entry by looking at the destination rob tag. We go to the entry of that rob, we index it, and then we write the result here. So what was the result? 1 times 2. So it was multiplier, right? So 1 times 2. So we write the result here. And but so this is note, this is R stage, writing to the reorder buffer. It is not W stage. So we write the result only in the reorder buffer here, right? And since the result is available in the reorder rob entry 0, provide its registration with the matching tag 0, right? So first what we did is that we wrote the result here in the reorder buffer, and then now since now result is available, what we do is that we see is there any instruction, any reservation station which has invalid source and has a matching tag, right? So we have, what is the matching tag? The matching tag is the basically entry 0. Do you see any in the reservation stations? Not in rat yet, only in the reservation station. So we have a matching tag here, 0. Do we have any matching tag? No. So we have this 0 matching with the tag this one, right? So since the result is now available in rob entry 0, we will provide the result to the reservation station with matching tag, right? So we provide the result here and we mark this result as valid. So since now it is valid, so both are the sources are available. The add instruction, the first add instruction is ready to execute. So it can enter the E1 stage. In the same cycle, this add instruction, second add instruction enters the R stage, right? So what we do is that we will look at its destination rob tag and using it index the rob. So it will reach the entry 2. So we write the result here 8, right? So 6 plus 2 is 8, right? And then we will see that is there any matching any in the reservation station tag, in the tag column, is there any matching tag which has the same value as the entry number? Yes, we have two, this one. So what we will do is that in the next, we will basically, not in the next cycle, in the same cycle, we will write the result, we will write the value here and we will mark this valid, right? So but still, this second multiply instruction is not yet ready to execute because one of its sources not available yet, right? And in the same cycle, add enters the E4 stage, and the last two instructions are still waiting, right? Because second last is multiply, and one of its operand is not available, and the last is add, and both of its operands are not available. Now, here is the difference. So remember, in our stage, for both instructions, we wrote the result only in the reorder buffer, and we only updated, based on the matching tags, we only updated the value and validity information in the reservation station. We didn't update the rat or register alias table here, right? We are going to do that. We are going to write the registers in the write back uh, step or stage. So in the write back stage, let me check the time. Yeah, we still have like, I guess, 15, 20 minutes. So in the write back stage, what we do is that we write the data, this value, into the destination register. What is the destination register? R3. So we write the value 2 in the R3 and we make this bit 1 to indicate that the result is written, right? So this is one thing. So we do two operations. The first operation is that we write the result, we copy the result from the destination register value field of the reorder buffer into the destination register, which is R3. So this was R3. We simply wrote 2 here, right? And we mark this bit 1 to indicate that yes, the result has been written in the register, destination register. So this is one thing. Second thing is updating this bit from invalid to valid. What is the condition for that? The condition for that is that the entry of the instruction, which is the oldest most instruction in ROB, entry number of that instruction, it must match with the tag field of the destination register. So what is the tag field of the destination register? 0. What is the entry number of the oldest instruction, which is now in the right stage? It is also 0. So it is a match, right? So it is a match. So we can mark R3 as valid now here. And since now we have retired this instruction, now in the reorder buffer, we mark this entry as invalid. Invalid means now we have written the result into the register file. We have marked the result as valid, and we are now going to the instruction is done. It has left the pipeline. Okay. In the same cycle, add enters the E2, and now here is the interesting thing. This instruction cannot enter the write stage. Why? W stage. Why? A commit stage or retire stage. Why? Because we can allow is only that instruction which is the oldest instruction in ROB to retire, right? So which one is the oldest? This one is already invalid, so we ignore it. The oldest one is this one, right? Which is basically the add instruction, this instruction here, this instruction. So, and the second add is second add was at index 2, right? Here. So it is not the oldest one. Who is the oldest? This first entry, which is basically reserved for first add instruction. And it is still executing, right? So we cannot allow the second add to enter the right stage. So it is stalled. It doesn't enter the right stage. So, but its remains available. So, what was the result? The result of addition was 8. So, the result is available in the reorder buffer, but we will not write the result back in the R7. We are not going to write it here in R7. See, we are still indicating it as invalid, right? The next add, it enters the R stage here. So when it enters the R stage, so what we do is, this was the third add, right? So we look at the destination ROB, it allow it, and using it, we index the reorder buffer entry table, reorder buffer. So we go to the entry number 3, and we write the result in the destination result field, which is 17, right? 8 plus 9 is 17, right? But we only write the result in the reorder buffer. We don't do anything else in the R stage, right? In the next stage, uh, what we do is that uh, wait a minute. Yeah, so sorry. In the same stage, what we do is also that we compare the entry number for this instruction with any tag values in the only in the reservation station. So we have one match here, right? So in what we do is that we update it now to be valid and provide the result 17. So this is basically the same result copied into the reservation station. Now both sources are available for the multiply instruction, so it can start executing. Uh, so it can start executing here. So it enters the E1 stage. Okay. Add instruction is still waiting because both of its operands are not yet available. So it is still waiting. In cycle 11, now we are already done with multiply. So add enters the E3. Second add, it cannot enter the W stage because it can enter only because it is not the oldest instruction in the reorder buffer. Same is true for the third add because yes, it has completed its execution. We know the result for it, which is 17, but it cannot we cannot write the result into the destination register R10. We see here we cannot write because it is not the oldest instruction in the reorder buffer. Who is the oldest? The oldest one is this one. Okay, so this is oldest. I'm just writing old here to indicate, right? And multiply enters the second stage of execution, and decode the last add is still waiting, right? In next cycle, it enters E4. There is no change here for the same reason because these two adds are not the oldest instructions. Oldest instruction is this add, which is still executing, and this multiplier enters E3, and this is still waiting. It is waiting for its operands to become available. In next cycle, this adds completes. So now its execution. So it enters the R stage. So we look at its destination rob tag and using it index the rob buffer. So we reach this entry and we put the result in the destination register value, which is 6. So 4 plus 2 was 6, right? And not only that, but we still not we are updating that. But not only that, we also compare the entry number with and look for match in the tag columns, right? So we have one match here, right? So we what we will do is that we replace it. So replace mean we provide the value here, same value 6, and we mark is that it as valid, but still this add instruction cannot execute because the second operand is still not ready, right? So there is no change for other instructions in this cycle. In cycle 14, this instruction add enters the write stage. So when it enters the write stage, we again do the same thing by looking at destination rob tag. We go to the ROB and we have the value 6. And now what we do is that now we will basically what we will do is that we will write the result in the register file. So we updated the result in the register file. In the previous slide, it was 5. Now we simply copy that result into the register file. Okay. So, and we mark it here 1 to indicate that we have written the result. However, uh, However, we do not mark R5 valid. Why? What is the condition for marking a register valid in the RAD? That its tag matches with the oldest with the instruction which is we are committing, right? So which instruction we are committing? This one. What is its entry number? It's 1. What is the tag of R5? It is 5. So there is no mismatch. There is no match. So we that's why don't mark it valid and we keep it as it is. Okay. Okay. So where were we? Yeah. And there is no change for these two instructions, and the multiply enters the E5 stage and add is still waiting, right? Now in next instruction cycle, we are done with first two instructions. They have committed already, completed, they have left the pipeline. Now the who is the oldest instruction? So now this one is the oldest in the reorder. So now it can commit, right? And again, if it can commit, we go and look at the destination rob tag in the reservation status. It is 2, so we go to entry 2, and we put the result here. So which is like 2 plus 6, 8, right? And then we write the result in the destination register R7 here, and we make this bit 1 to indicate that the result has been written, right? So, but not only that, the second thing we need to do is that we look in the tag column of the rat for a tag which matches with the entry number of the oldest instruction. So we have a match too, right? So what we will do is that we simply now we will mark it valid. Okay, we mark it valid and we mark this entry in the rob invalid, right? Now the oldest instruction is the next one. So here it enters the E6, right? So it's mean that its execution is now completed. So okay. Then in next cycle, the oldest instruction is this one, right? So we look at its name of the destination register R10. So we write the result in the R10, right? 17, how is 17 calculated? It is simply 8 plus 9 because this was summation, right? And then we indicate that the result has been written. And the other thing we do is that we look for a match in the tag column, right? So we found a match. So what we do is that we will mark register R10 as valid, and we will mark this entry as invalid by putting it 0 here, right? So multiply has completed its execution. So now it can enter the R stage. So using this destination tag 4, we go to the reorder buffer, right? And in the destination value field, we write the result, which is result of multiplication, which is 8 times 17, which is 136, right? But we write the result only in reorder buffer at this point, not into the registers. We write into the register in W stage. And then we also look for a matching tag in the reservation status. So we have one match. So we mark it as now valid, and we also copy the value 136. Now both operands are available. So this next add instruction is ready to enter the E1 stage. In the next cycle, your multiply enters the commit stage. So for commit stage, what we do is that we look at the destination register and we write the result into the destination register, right? R11, right? So we have a match. No, no, sorry, we don't do that. We actually okay, yeah, sorry. So we do two things. First, we write the result into the destination register 130 or 136. We write it into R11. This is one thing. Second thing is we compare the entry number with the tag field in the RAT, right? So we have one match, and in that location we update validity bit to be 1, and we then mark this entry to be invalid, right? Now, which one instruction is the oldest one? This one, this is the oldest one, right? But it is still executing, so it takes four cycles to execute, and then it enters the R stage. So when it enters the R stage, the result is written in the reorder buffer, right? And then when it enters the W stage, we write the result back into the destination register, right? One thing, and we mark that, okay, we have written the result. The second thing we do is that we compare the entry number with the tag column. So we have match at one place. So at that place, we mark that now the register is valid, and we mark this entry as invalid. Okay. So with this, we are done with the uh, simulation of executing the program using the reorder buffer. Now, how it is different? So now if you look, our program is fetched and decoded in order. It is executed out of order, but its retirement is in order. How you can see? So first, you can see the order is indicated here. So all the instructions are entering in order. The blue, they show the order in which the instructions are committed. So they are committing in the same order as the program order, or like fetch or decode order 1, 2, 3, 4, 5, 6. However, the execute order is different. So first instruction A uh, and B, these two instructions complete their execution in the same cycle, cycle number 9. Then instruction sorry, if I want to name them, so A and C complete their instruction in cycle number 9. Instruction D completes its execution in cycle number 10. B completes execution in cycle number 13. right? E executes the execution, completes execution in cycle number 16, and F completes the execution in cycle number 20. So the execution is still out of order. So we still have that advantage of out of order execution because it allows us to let the younger independent instruction to execute without waiting for older instruction to complete its execution. However, we now meet the requirement that retirement should be in order, right? Here you can see 1, 2, 3, 4, 5, 6, right? So this is how your in order reorder buffer is used in out of order execution, where it allows out of order execution to achieve the commit stage or the write back stage according to the program order. So I'm not reading this summary. You can do it on your own. So because I think I'm already running out of time. So now uh, let me share with you the code for accessing the access code for the uh, so the code is 739284. I repeat, 739284. Let me let me also make sure that you can see it. I don't know whether yeah, you guys can see my screen, right? So the code is here, this one, 73924. If you want, I can make the font bigger. 739284. Okay. So that was the lecture. And if you have any questions, I know, I mean, it is not possible for you to answer the questions because it is a recorded lecture. So what I will do is the following. If you have questions after watching this video, mention those questions in the class participation form, question number 2. Uh, Question number 3, leave it empty. I will give 20 points to everyone, right? But you need to answer question 1, question 2, and question 4 of the class participation form. Thank you.